Hello everyone, welcome to today's class. Let's continue with our topic of complex number. We'll start with the polar form. Okay, so what is a polar form first of all? Before discussing that, I need to discuss two terminologies. First is modulus of the complex number z, that is represented by, of course, mod z. Okay, so for understanding that, first of all, what's our z? Z is a plus iota b. Okay, let me put the heading like this, modulus of z. Okay, so z is a plus iota b, then mod z is nothing but square root of a square plus b square. Okay, right now this is just a straightforward formula. I'll explain you the meaning of this when we'll talk about the polar form. For now, this is the formula. Okay, mod z is square root of a square plus b square. Okay, and then we have to talk about another term, that is argument of z, usually represented by theta. Okay, that I cannot give you a straightforward formula because it's a situational based idea. So first of all, let's see what is this modulus of z and where is this argument, and overall what is the overall sense for this polar form. Okay. Okay, so first of all, it's pretty much like a coordinate. If we draw this complex, if you want to represent this complex number, first of all we need a separate plane. We cannot show this on number line because it's not a real number. So we draw a separate plane that is known as Argand plane. Okay, it is used to represent complex numbers, and this is the x-axis. Okay, and it is known as real part of z. This is the imaginary axis, img part of x. Okay, so instead of x-axis, y-axis, you have two axes. One is real part of z, one is imaginary part of z. If we look at z, z was a plus iota b. This was the real part of z. This was the imaginary part of z. Okay, so let's plot this. So real part is a, so some length a. Okay, imaginary part is b, so some length b. So basically, if we take this length as a and if we take this length as b, this particular point represents your complex number z is equal to a plus iota b in complex plane. Okay, it is pretty much looking like a x-axis y-axis. Now suppose like a comma b was the coordinate, so it is pretty much like that. This is your complex number z. Okay, z, which is a plus iota b. Okay, this is what is representing. Now let's talk about this root a square plus b square. It's looking like a Pythagoras. It's like hypotenuse expression. Look at where is your hypotenuse in this. This particular length is mod z. Okay, and now first of all, this complex number z, it is making some angle with this x-axis, or should I say real axis. Okay, so this angle is your argument known as theta. Okay, now for the simplicity, you can see this theta is nothing but, if I take tan, this is tan theta is equal to b by a. But it's not always that simple, because not every time you will get this complex number in the first quadrant of Argand plane. It can be in the second quadrant, third and fourth also. So finding the argument, it's slightly the tricky part. Modulus is, you can directly find it by formula also, and meaning is also very much straightforward. Okay. Fine. So I hope you get the idea that what we have to do regarding this argument and some idea regarding how to find it. Now let's take few examples to explain how we can find it. Okay, regarding theta, this complex number can be in the second quadrant here also, in the third quadrant here also, in the fourth quadrant here also. In that particular situations, remember I asked you to calculate the angle always with the positive x-axis. Okay, so this will be like this. Okay, we can do that, but it's just that the convention says that the principal value of this argument is usually denoted in minus pi to pi. So first of all, your theta can be, of course, simple idea is that theta can be in 0 to 2 pi. So that is pretty much same as solving your trigonometric equation. The same idea will be used, but okay, but theta, principal value of theta, means standard value as such, principal value of theta or argument as such, it is defined in minus pi to pi. I know it's slightly change in convention, but this is how it's actually defined. Theta can be in 0 to 2 pi also if nothing mentioned, but the general idea is that we always take theta in minus pi to pi, not 0 to 2 pi. Now this complicates things slightly because we already know how to calculate these sort of angles, but how to calculate now the argument for this. So I'll give you 4 examples for each and every quadrant. That should pretty much clarify all the things regarding this theta, how to get theta in minus pi to pi, because I know you can find this in 0 to 2 pi, but restricting the angle in minus pi to pi, there's one trick that I'll explain you. Okay, so let's talk about that particular trick. I'll write it here only. I think diagram effectively is needed. So in order to find this, I hope it is visible. I'll take some more space. I'll draw it here. So in order to find the argument, first of all, use this diagram. This will help you a lot. So if your complex number is in the first quadrant, it should be blank. Let's take if suppose the complex number is in the first quadrant, then your theta will be equal to alpha. I'll talk about alpha. What is alpha? If your theta is in if your complex number is in the second quadrant, then in that case your alpha will be basically this angle, but your theta will be pi minus alpha. I'll talk about what is pi minus alpha. If your complex number is in the fourth quadrant, you'll take your theta as minus alpha, and if it is in the third quadrant, then your theta will be minus of pi minus alpha. So basically you remember only these two values, alpha, pi minus alpha. Below it, it will be minus alpha. Below it, it will be negative of pi minus alpha. Okay. Now, what is alpha? What's the point of alpha? Okay. Alpha is tan inverse p by a in the mod. Okay. So you first of all always calculate your alpha, then decide the quadrant. According to the quadrant, decide your theta. Let's take example that will clarify this in a slightly better way. Let's take one example. Question is express 1 plus iota in polar form. Okay. 1 plus iota, 1 minus iota, minus 1 minus iota, minus 1 plus iota. So 4 questions, 4 different quadrants. This will explain you everything. Okay. Okay. One second. All right, let's solve the first one. First one, 1 plus iota. Okay, I haven't talked about the format of polar form, no? No. Okay, so let me tell you the format. It's just a format as such. So effectively now we can talk about polar form. So your polar form is any complex number will be represented like this: r bracket cos theta plus iota sin theta. Okay, and what is this r? This modulus is known as r. Okay, modulus of z also known as r. Okay, so in this polar form is represented by this. So we need to calculate only the value of r and only the value of theta, and we have to write like this. That's it. That's the way of polar form. It's as simple as that. Okay, a lot of information. Let's solve the questions because that will explain what we have to do. So in order to find the polar form, first of all calculate r, which is modulus of z, which is, what's your a and b in this? A is 1, b is coefficient of iota, which is again 1. So square root of 1 square, that's square root of 2. Okay, second step, this is your first step. Second step, in order to solve, you calculate first of all alpha. Alpha is tan inverse modulus of b by a. Right now both are positive, so modulus has no effect. 1 by 1. What is tan inverse 1? 45 degree, that's pi by 4. Now third step, quadrant. Which quadrant of Argand plane? For that, try to plot it. Okay. This is the real axis, this is the imaginary axis, IMGX. So A you have to plot on x-axis and B you have to plot on y-axis. Basically consider this as a coordinate 1, 1. 1, 1 will be in the first quadrant. Okay, that's your complex number. Now for first quadrant, what was the theta? Theta was equal to alpha. So directly you can say theta is equal to pi by 4. And finally your polar form is r bracket cos theta plus iota sin theta. Put the value of r, that is root 2 cos pi by 4 plus iota sin pi by 4. Okay, that's it. Don't solve this, because if you put the value of cos pi by 4, sin pi by 4, you will get nothing but 1 plus iota. This is the representation known as polar form. That's it. So for that, just follow these 3 steps. Step 1, find r. Step 2, find alpha. So far just formula based. Step 3, locate the quadrant. Okay, use a and b as a coordinate and try to locate the quadrant. You can directly judge it. Not you don't always need to plot it. If you can directly judge by looking at the coordinates, it's good. Okay, and for that particular quadrant, I gave you this form that for first quadrant theta is alpha, for second quadrant theta is pi minus alpha, for fourth quadrant theta is minus alpha, for third quadrant theta is minus of pi minus alpha. Okay, I'll highlight this. Okay, let's solve for the second quadrant. That what was given. Second question was 1 minus iota. Okay, second one was 1 minus iota. So let's solve for it. Again, same 3 steps will follow: r, alpha and theta. First step, r. For first of all identify a and b. A is 1, this time b is minus 1. Coefficient of iota is minus 1. R is mod z is equal to square root of a square b square. That's, I'm directly writing root 2. Okay. Now second step, alpha. Alpha is tan inverse modulus of b by a. So tan inverse modulus of minus 1 upon 1. Mod makes everything positive. So tan inverse 1 again pi by 4. Third step, locate the quadrant. So for third one, this is basically 1 comma minus 1. 1 comma minus 1 is in the fourth quadrant. So this is where your complex number is. So basically your complex number is in the fourth quadrant. For fourth quadrant, theta is minus alpha. Now you see, basically we are restricting. If I calculate this theta from positive x-axis, it will be more than pi. And the principal value of theta, the standard, is considered to be in minus pi to pi. So theta is minus alpha. So I can rewrite. So theta is minus pi by 4. Now just write down the polar form. That's r bracket cos theta plus iota sin theta. R is, what's r? Root 2. Cos of minus pi by 4 plus iota sine minus pi by 4. And that's it. You don't solve it any further. That's your answer of polar form. Okay. Now let's quickly solve third and fourth one. Third one was minus 1 minus iota. Pretty much you can guess. This is in third quadrant, minus 1 minus iota. So this time I'm going to be slightly quick about this. R is, A is 1, B is 1, R is root 2. You can calculate, same thing. Okay. Then theta is equal to tan inverse, sorry, A is minus 1, B is also minus 1. So tan inverse, again it will come 1, it will come pi by 4 because modulus is there. And if I locate it in quadrant, it's in which quadrant? This is minus 1 comma minus 1. This is in third quadrant. So complex number is in third quadrant. Your theta is minus of pi minus alpha. So minus of pi minus pi by 4, that's minus 3 pi by 4. Okay. Now finally your polar form. R cos theta plus iota sin theta. So root 2 cos of minus 3 pi by 4 plus iota of sine minus 3 pi by 4. That's your answer. This time I was quick. If you want, you can attempt on your own with a slow pace. Just follow the 3 steps because I'm repeating the same idea for all the 4 parts. Just I'm locating the main part, that is your argument, how to calculate your argument. This is why I'm discussing all the 4 quadrants. Fourth one was minus 1 plus iota. Again, A is minus 1, B is 1, R is again root 2, alpha is tan inverse, again mod of minus 1 upon 1, that's pi by 4 again. Then locating the quadrant, this is minus 1 comma 1. Pretty much this is second quadrant. Okay. So your complex number is in the second quadrant. In second quadrant, theta is pi minus alpha. So pi minus pi by 4, that's 3 pi by 4. Okay. This is done. What else is need? Polar form. R bracket cos theta plus iota sin theta. That's root 2 cos 3 pi by 4 plus iota sin 3 pi by 4. Okay. So this is regarding polar form. The question will always be regarding either finding polar form, or in MCQ what they can do is they can ask for just the argument, or they can ask you for modulus. Modulus is very easy. So maybe not modulus, but maybe they can ask you for the argument. So argument, this is the idea, one of the easiest idea. Calculate alpha according to quadrant. I gave you what is theta. Just learn those 4 values. It's as simple as that. That covers your polar form. Effectively, this was the whole topic. I hope it is clear. You can take different values also. It's not necessary that always 1 minus iota, 1 plus iota will come. Root 3 plus iota, 1 plus root 3 iota, they can also come. Okay. All right. So this is done. All right. Let's move to the next part of complex number. That is properties of some complex numbers, and I'll introduce one more thing here. Okay. So for the properties of complex number, first of all, there is modulus that we already know. There is properties of those, and there is one more thing known as complex conjugate. So one more subtopic, complex conjugate. It is represented by z bar. Okay. So as per the definition goes, if z is a plus iota beta, z bar is nothing but a minus iota beta. Means you just change the sign of this iota. Whatever term iota has, if it is plus 3 iota, you write down minus 3 iota. If it is minus 3 iota, you write down plus 3 iota. Don't do anything with the real part, just change the imaginary part, sign of the imaginary part. Okay. So it's as simple as that. Suppose z is 3 minus 4 iota, so z bar will be 3 plus 4 iota. Change the sign of iota part. That's it. Okay. Now properties, let's talk about that. So first properties. First, z into z bar is mod z square. You can verify this. A plus iota beta into a minus iota beta. It will become a square plus b square, which is nothing but square of modulus of z. Okay. Second thing, that you can split the modulus of two complex number in multiplication. Modulus of z1 z2 is mod z1 mod z2. Third, same thing can happen in division also. If two complex numbers are being divided and you have to calculate the modulus, you can do it, calculate the modulus of each number and then divide. Okay. Fourth is regarding complex conjugate, that is we can split complex conjugate in two parts. So z1 plus z2, the complex conjugate of that is z1 bar plus z2 bar. Same thing we can do about minus also. Z1 minus z2 complex conjugate is z1 minus sorry, z1 minus z2. 4 5. Sixth, we can split regarding around multiplication also, like complex conjugate can be splitted around z1 z2 like this, about the product also, and they can be splitted about division also. z1 z2 complete bar or conjugate of it is z1 bar upon z2 bar. This is done, this is done. And one more, if you take complex conjugate 2 times, you will get original complex number. So basically change the sign one time, change the sign another time, you will get back to the original complex number. This is pretty much all the properties regarding this, and this is not a property, just be careful about this. z1 plus z2 plus or minus, modulus of that is not always equal to z1 mod plus minus z2 mod. Means you cannot split modulus about plus and minus. Sometimes it may work, sometimes it may not. Okay, so be careful around this. This is not possible. Modulus can be splitted in multiplication and division only. This complex conjugate can be splitted anyway, multiplication, division, addition, subtraction. Okay. All right. Now that we have done the properties, there are a few questions sometimes related with these properties. and a few other ideas. So let's discuss those ideas of complex number through questions. Okay, this is one good question. It combines two topics, your complex number as well as your this trigonometric equations. He is saying find real value of theta such that this is purely real. Now what is the meaning of that being purely real? Okay, so something is purely real means z is, see, any number, complex number can be represented like this. So if your b is 0, then z is a, complex number is a. This is called purely real. And if your a is 0, so your complex number will have only imaginary part, iota b. This is called purely imaginary. Okay, so do remember these conditions. What is the meaning of purely real and purely imaginary? Okay, so he's asking us to find theta such that this is purely real. So for this, first of all, this is not in a plus iota b form, so we have to convert this. I'll rewrite the question if it's not clearly visible. 3 plus 2 iota sine theta upon 1 minus 2 iota sine theta. Now first of all, we have to always rationalize the iota part in the denominator. We cannot deal with any complex number with iota in the denominator, so let's rationalize it. Change the sign, multiply with 1 plus 2 iota sine theta, 1 plus 2 iota sine theta. Okay, let's multiply. Denominator is very simple, a square minus b square, so 1 square minus 2 square is 4, iota square is minus 1, so change the sign, and sine square theta. Okay, multiplying numerator, so we have to multiply through basics. So 3 multiplied by 1, then 3 multiplied by this 2 iota sine theta, that is 6 iota sine theta. Okay, then multiply 2 iota sine theta with 1, so 2 iota sine theta again, and then multiply with this. So 2 iota becomes 4 iota square sine square theta. Okay, basic multiplication. Add them. These two can be added, and this iota square, solve this. This is minus 1, so it becomes 3 minus 4 sine square theta. Keep it as it is. This is the part which does not have any iota in it, and the iota part is 8 iota sine theta. Okay, upon, I'm splitting the denominator, 1 plus 4 sine square theta, 1 plus 4 sine square theta. Okay, now the question says it has to be purely real. Okay, for that b has to be 0. That means this part of iota, should be 0. This is the idea. Now let's work on that, because I'm not saying this, the question is saying this, that you need to find theta for this, for which this is purely real. That means this part should be 0. So basically 8 sine theta upon 1 plus 4 sine square theta should be 0. So denominator, take it here, because it can never be 0, so multiply this, so you'll get 8 sine theta is 0. Now that gives you sine theta is 0. Now sine theta is 0, how do you solve this? This is nothing but a trigonometric equation. I told you that you have to give, if nothing mentioned, you try to give your answer in general form. Okay, not just the principal values and everything. So if you can recall how we used to write, so theta is n pi plus minus 1 raised to power n, and then principal value. What is the principal value? Means just give me one value in 0 to 2 pi for which sine is 0, that is 0 itself. So theta becomes n pi, where n belongs to z. That's your answer. So for theta equals to n pi, this particular complex number is purely real. Okay, just remember this idea: purely real, the complex part has to be 0, purely imaginary, the real part has to be 0. Okay, all right, now a few simple example based on modulus and complex conjugate. That's okay. Okay, let's look at this question. He's saying z1 is 2 minus iota, z2 is 1 plus iota. You have to find modulus of something like this. Okay, so that expression is z1 plus z2 plus 1 upon z1 minus z2 plus iota, and you have to calculate modulus of this. It does look slightly complicated, but let's put down the values of z1, z2. Okay, so that is 2 minus iota plus 1 plus iota plus 1, and this is 2 minus iota minus z1 is 1 plus iota. Remember to put a bracket here for z2 plus iota, and you have to calculate modulus of that. So solve this. Numerator will become, this will cancel, and denominator will have to open the bracket first. This will become 2 plus 1 plus 1, 4, and this becomes minus 1 minus iota. Let's open the bracket first. 2 minus iota minus 1 minus iota plus iota, and everything is in modulus. Let's solve further. 4 upon, see, iota cancels, 2 minus 1 is 1 minus iota and modulus. Now we know we can split the modulus of numerator and denominator. Okay, so you don't have to rationalize this because he's not asking for the complex number itself, he's asking for modulus of it. So let's split modulus of 4, modulus of 1 minus iota. What is modulus of 4? 4. Okay, what is modulus of 1 minus iota? That is square root of 1 square plus minus 1 square, a square b square. So that is 4 upon root 2, or you can write down this itself as 2 root 2. Okay, so put down the values, and what I have done is use the property here. What is the property used? That z1 upon z2 modulus is mod z1 mod z2. That makes the question slightly simpler. Okay, all right, next question. Next one says you have to find the real number x and y such that this multiplication is conjugate of this. So let's first calculate the conjugate of this expression itself. Minus 6 minus 24 iota. Okay, this one. What is the conjugate of this? That is minus 6 plus 24 iota, and this should be equal to this multiplication x minus iota y, 3 plus 5 iota. Okay, let's see how we can solve this. Let's multiply this. So you'll get 3x plus 5x iota. Let's multiply first x then iota, minus 3 iota y, and minus plus becomes minus 5. Okay, 5 I've written, minus 5 minus 5, where was it? Minus 5 y iota square is equal to minus 6 plus 24 I. Okay, let's solve this. 3x as it is, this becomes, we cannot do anything about this, let it be. So iota into 5x minus 3y. Okay, this is plus 5y equal to minus 6 plus 24 iota. Okay, now combine this, 3x plus 5y plus iota into 5x minus 3y is equal to minus 6 plus 24 iota. Now how can we solve this? The idea is to compare the real part with real part, means term without iota with this, and compare the complex part or the iota part with iota. If you compare this, you'll get two equations, 3x plus 5y equal to minus 6 and 5x minus 3y equals to 24. So you can solve this, I think. So I'm not solving this because the idea is pretty simple here. Solve the two equations, get xy. Okay, so I'm not solving this, it's pretty standard here because the idea how to generate the condition was much more important here. So the idea is to compare real part with real part, imaginary part with imaginary part. Okay, the rest you can solve. Okay, 18th is a good one to you. Okay. Okay. So this one is saying modulus of this should be 2 raised to power x. So let's take modulus of this. So modulus of this becomes, it's a very simple question, root 2. Okay, power x is 2 raised to power x. Root 2. So that becomes 2 raised to power x by 2 is equal to 2 raised to power x. If base is same, power should also be same. So x by 2 should be equal to x. Okay. Can we really solve this? So take this to the other side. X minus x by 2 equal to 0. X by 2 equal to 0. You'll get x equal to 0. Means as such there is no number which can satisfy this condition. You just use your common sense. How can something full be equal to the half? Up unless and until it is 0. Yeah. So yes, x value is 0. And let's see what is the question saying. The question saying find the non-zero integral solution. We cannot find that. We were not able to find that. So find, and he's not even asking us for the solution. He's saying find the number of non-zero solutions. How many non-zero solutions is there? I have one solution that is 0. So number of non-zero solutions is 0. The value of x is also 0, but that's a 0 solution. He's saying non-zero solution means non-zero integral solution means 1, 2, 3, any value of this. There is no such value which will satisfy this. Any number 1, 2, 3, 4, 5 will not satisfy this condition. So there is no such solution present. That means number of non-zero solution is 0. Okay. Interesting. I mean, that particular question, even if you misunderstand it, there is a good chance that you will be able to do that. You can get lucky. All right. Last one. Yeah, this is a very good question. First of all, this will use all the properties that I talked about complex number. And the idea is also very unique to find this. He's asking us to calculate this. We don't know anything about the number this time. So far you have done all the question in which alpha, beta, the complex numbers were somehow given. This time he is saying alpha and beta are two different complex number. Okay, we are saying mod b is minus 1. This beta complex number is modulus of that is 1. Okay, he has not given us complex number directly. He is saying find this. We don't have alpha, the first complex number. We don't have even beta. All we have is modulus of b. So let that this value comes out to be some p. Okay, and I'm squaring both sides. Now the idea is, remember one property that z into z bar is mod z square. So I'm using this in reverse, that modulus of this beta minus alpha upon 1 minus alpha bar beta is product of the complex number and product of our bar. That means product of b minus, I'm writing alpha like this, okay, otherwise it will look like a, upon 1 minus alpha bar beta, this into the complex part of it, b minus alpha upon 1 minus alpha beta, sorry, alpha bar beta, complex part of it, the product of these two should be this expression, and which is equal to p square. That's the first key step in this. So first property is being used. Okay. Now we can split this complex conjugate in numerator and denominator. So b minus alpha upon 1 minus alpha bar beta, it is b minus alpha bar, numerator we have split conjugate, and denominator also 1 minus alpha bar beta complex conjugate. Now complex conjugate can be splitted about plus minus also, multiplication. So we have to do, this is b bar or beta bar alpha bar upon 1 bar minus alpha bar beta whole bar. Okay, so this becomes b minus alpha 1 minus alpha bar b, let it be b bar, let it be alpha bar. We are focusing now on this alpha bar beta whole bar. So conjugate still can be splitted. Okay, one is not even a complex number, so 1 bar will be 1 itself, because for calculating bar or conjugate we have to change the sign of imaginary part. There is no imaginary part, so 1 bar will be 1. So this becomes alpha bar bar and beta bar, and alpha bar bar is alpha itself. So I'm removing this alpha bar bar and writing this as alpha only. Now let's multiply. So basic multiplication, b into b bar, b into minus alpha bar, so minus alpha bar beta, then alpha minus alpha into beta bar, then minus alpha into minus alpha bar, that is plus alpha bar. Denominator, let's multiply, 1 into 1 1, alpha bar beta 1 into minus alpha beta bar, then alpha minus alpha beta bar into 1, sorry, and lastly negative negative, alpha alpha bar beta beta bar. I know it's looking slightly ridiculous, lot of terms are there, but trust me, it's just about to get solved because all the properties are now being applied. B into b bar is mod b square minus alpha bar b minus alpha beta bar. Alpha into alpha bar is mod alpha square upon denominator, let it be alpha beta bar minus alpha bar beta, and use this. Alpha alpha bar is mod alpha square, beta beta bar is mod beta square. Okay, and we know that mod beta is 1 as per the question, so I'm replacing this and this with 1. So 1 minus alpha bar b minus alpha beta bar plus mod alpha square upon 1 minus alpha beta bar minus alpha bar beta minus 1 into anything is same, so alpha square. Just look at the numerator, 1 1, alpha bar beta alpha bar beta, alpha beta bar alpha beta bar. Sign, there is something wrong with the sign. Negative negative, this should be positive, this should be positive, this should be positive. Now the signs are matching. So yeah, 1 matching with 1, alpha bar beta alpha bar beta, alpha beta bar alpha beta bar, mod alpha square mod alpha square. Numerator and denominator, they are same, so this becomes 1. Okay, so but I think this whole expression was p square, na? Okay, 1 second, I have to talk about this. So this is p square. So if p square equal to 1, what is p? Plus minus 1, but we'll consider reject negative. Why? So p is 1. Why we have to reject negative? not just because this is negative, because what is the thing we are calculating? We are calculating modulus of something, and modulus of something has to be positive. That's why I'm rejecting negative. Okay, because modulus of any complex number is positive. It cannot be negative. That's it. So very weird idea for this particular question, but the whole idea for this particular question is that you got comfortable while applying the properties, like you split the complex conjugate about numerator and denominator, then about plus and minus, then alpha bar becomes alpha, and then after that it's standard multiplication. The idea is to use just the properties of complex conjugate and use this property in reverse. That's a good idea. Okay, so always the quality questions will be looking like this. Okay, it will have unique ideas. One common question comes that how can we know the new approaches? You cannot. In the first go, you will not be able to generate new ideas directly, but once you go through these kinds of questions, then your mind will have slightly broader vision that yes, there are few questions that can be done like this. Maybe this can work around, or some particular step might be useful in any particular question. Okay, so few questions are just application, few questions are from learning point of view. This is one of those questions. Okay, all right, and this is done. Last thing that I want to discuss is properties. No, not the property, square root of complex number. So I'll just discuss the idea, then you can apply it in any question. Let's take, suppose you have to calculate square root of 1 plus iota. This comes. Okay, so it has to be some complex number, a plus iota b. We have to calculate this. Now the idea is you square both the sides. So 1 plus iota is, squaring this will get a square plus iota b square, iota square b square plus 2ab iota. So 1 plus iota becomes a square minus b square plus 2ab iota. And I told you how we can generate equation, compare the real part with the real part. Compare the complex one with complex iota I missed. Okay, so clearly we get a square minus b square as 1. This is our first equation. And 2ab also as 1. This is our second equation. Okay, now the way you can solve this is by getting the value of a and putting in this equation and then solve it. Yeah, this can be one way. I'll give you another approach. Okay, you can try to solve this. See, you have to solve this equation. How you solve is up to you, but I'm giving you one approach that will help you to simplify any kind of question with these kinds of equation. So how do we solve this? We are using a property here. Those who have somehow studied with the ICSC, they must know this property. The property goes like this: a square minus, plus b square whole square. It will be a square minus b square whole square minus 4a square b square. Okay. Now why is this so helpful? Let's see. A square plus b square whole square, we don't know. A square minus b square, we know that's 1 square minus 4 a square b square is this value 2ab. If we square this, we get 4a square b square. So that's again 1. Sorry, this is plus. No, is equal to 2. So this becomes a square b square is nothing but square root of 2. Why I'm not taking plus minus? Again same idea, a and b are real numbers. Square of that should be positive, so it cannot come negative. Okay, so a square b square whole square is 2, so a square plus b square has to be root 2, not minus root 2, because square of two numbers cannot be negative when added. Let's consider this as a third equation, and now the benefit is you can so much easily solve the first and third equation. That's why this particular identity is so helpful. A square minus b square equal to 1. A square plus b square is root 2. Add them, you'll get 2a square as root 2 plus 1. You'll get a square as root 2 plus 1 upon 2, and you will get a as plus minus root 2 plus 1 upon 2 inside a square root. A particularly can be negative as well as positive. That's why I'm considering it plus minus this time. Why I'm not considered here? Because a square b square has to be positive. Okay, so this is done. A, so same way, my recommendation is not to put the value of a and find the value of b. My recommendation, go for another solution. Equal to 1, a square plus b square equal to 2. Solve it again. This time change the sign and solve it. So minus 2b square is 1 minus root 2. So because putting the value, it will complicate a thing a lot. So this becomes b square is equal to root 2 minus 1 upon 2. B again will get plus minus root 2 minus 1 upon 2. That's your a, that's your b. If you can find now, since you have found a and b, that's your final answer, that the square root of this complex number is a plus iota b. So just write down that square root of 1 plus iota is plus minus square root of root 2 plus 1 by 2 plus minus iota times root 2 minus 1 upon 2 square root. Yes, it is complicated. Okay, but in the exam, slightly easier question can come. Just calculate the square root of I. For that particular question, you don't have to solve this much because the equations are actually simpler. Okay, let me show you. Let again same idea. This is a plus iota beta. Square the both side. So iota is a square minus b square plus 2ab iota. Now if you compare, there is no real part. So you'll get a square minus b square equal to 0. That gives you a very interesting a square is equal to b square. Okay. And this is the first equation. No? And second equation, you can get 2ab is equal to 1. Okay. If a square is equal to b square, you can get a is plus minus b. It can be equal to b also. It can be equal to minus b also. So accordingly, you can get it here. If you put a, replace it with b, so you'll get 2b square equal to 1. So b is plus minus 1 by root 2. And similarly, you can get a as also plus minus 1 by root 2. Even if you put negative, let's see what happens if you put negative. I've replaced a with b in this equation. If we replace a with minus b, let's see what happens. 2ab equal to 1. So minus 2bb minus 2b square equal to 1. B square minus 2b square equal to 1. So b square is minus 1 by 2. Square of any number cannot be negative. No solution for this. Okay. So a is coming plus minus 1 by root 2. B is also coming plus minus 1 by root 2. So I can say square root of I is plus minus 1 by root 2 plus minus 1 by root 2i. Okay. That's how you can calculate. This can be so much easily be given in an MCQ exam, but for subjective one, this one is slightly lengthy, but a subjective one, but again can be given in an objective exam also. So if you learn this identity particularly, it will help you to reduce this time for solving this kind of equation. Okay, this one was, I think, pretty much easy here. Square root of I. Okay. All right, fine. All the properties are done. Polar form we have done, and now square root of complex number is also done. That pretty much take care of this chapter. Okay. So that's it for today's class. See you in the next class. Good day, everyone. Bye.